Okay, this is going to be a bit of a longer video. I'm going to talk about the logistic equation. Often this is introduced as a fairly elementary model of population, where the population is limited by some resources. It's a first order, nonlinear, so this is first order. Nonlinear because we have a p squared. But we've only got p terms on the right-hand side. We don't have a t term, so this is actually easily separable. So we can solve it. We're given an initial condition. As well, that is, we've got some starting population. Now, a couple of other terms that I'd like to draw your attention to. This k thing is often called the growth constant. And this k, the capital K, that's sometimes called the carrying capacity, or let's see. We'll just call it the carrying capacity. It's related to the maximum amount of resources, or the maximum population. And we'll analyze that in more detail later when we learn about stability. For now, this is just a complicated equation that we can solve with separable techniques. So we're going to go ahead and do that. Separable. So I'm going to leave the little k on the right-hand side. Write this 1 minus 1 capital K dt. So that's just rearranging, assuming that these little infinitesimals can be multiplied across, and we're going to sort of legitimize it all by putting integral signs on it. You'll notice that the right-hand side integral is trivial. It's going to go to kt plus a constant. However, the left-hand side one's a bit of a pain. So we'll have a look at the left-hand side first. The first thing we're going to do is we're going to rewrite it like this. Okay, so that's just by multiplying through by k over k, right? So k over k equals 1, yeah? So when we multiply through by this k over k, we don't actually change the equation at all, because it's just multiplication by 1. But it lets us cancel out this fractional term, this sort of second fraction in the denominator, which is a bit of a nuisance. So this is the equation we now have to deal with, or the integral we have to deal with. The denominator is a rational function. We've got two factors, or the integrand is a rational function. The denominator has two linear factors which are not repeated, so we can use partial fractions to break this up. So if you're a bit wobbly with partial fractions, you can go back and see the other videos that I've recorded on that. Essentially what we're trying to do is take our fraction k on k over p into k minus p, and rewrite that as a on p plus b over k minus p. We can multiply through by the denominator to clear that out. K equals a into k minus p plus b p. That's what happens when you multiply through by the denominator. And this expression must hold for any value of p. And we know that if we select some particular value of p, we can use cleverly chosen values of p to determine our constants. So let p equals 0, k equals a, k, the minus p disappears and the bp disappears. That implies a equals 1 when we divide through by k. Okay, let p equal k now. So that means that this factor disappears. So we've got k equals a times k minus k, that's 0, so that a term disappears, and I'm left with bk. And that implies that b is equal to 1. So we've very quickly done a partial fraction decomposition of this thing, and we've discovered that k over p into k minus p, we've discovered that's equal to 1 on p plus 1 over k minus p. And now we can substitute this back into the integral. And now we can approach this integral quite easily. All we have to do is remember how to integrate 1 over p and terms of that form, and we remember that they go to logarithms. So the first part of this integrand gives us natural log absolute value of p. The next bit gives us log absolute value of k minus p. But remember, we've got this minus sign here, so we've got to be careful to take care of that. Now, normally you'd have a constant of integration, but remember this is a separable ODE, and we're free to put our constant of integration on either side of the equation. So I'm going to associate the constant of integration with the other integral. So now what we have log abs p minus log abs k minus p. You recall that that's equal to this, right? Just to show you where I'm at. This is the equation we started with. We've done the left-hand side integral. Now we've got to do the right-hand side integral. And that's where I've included our constant of integration. All right. So we've made good progress on this. What we now have to do is rearrange the expression so we have p all by itself. So recalling our log laws, again, how to manipulate logarithms. If you see 2 logs subtracted, that's like the 2 logs divided. So we've got this, and now we can exponentiate both sides. And now we can use our exponential law to separate out that constant of integration. So this is so now we've got this constant of integration. We can use the plus and minus trick that you would have seen in some previous videos that I did on separable equations. Just remember that the absolute value is either plus or minus the argument, depending on whether the argument's positive or negative. Plus and minus, multiplying through by that, it's still just a constant. So we can actually disguise the plus and minus and the absolute values by hiding it in some constant called A. Okay, so we're not done yet. This is still in the wrong form. We've just got to go ahead and rearrange it. The fastest way to rearrange it is actually to turn it on its head. So invert this thing. Obviously, if you're doing this for the first time, you don't know the sort of tricks and steps, so you might multiply across and so on. I'm just doing it a sort of more transparent way because I've done it before. Okay, so that's just rearranging. Now we flip it on its head again. And that's what we get as our solution. Remember that A is a constant of integration, so this is the general solution. At t equals 0, p equals p naught. So p naught equals k over 1 plus a. At t0, that exponential is just 1. So now we can rearrange for a. Okay, so that's just swapping the denominator with the other side, and then dealing with the plus one, the minus one. All right, so this gives us our particular solution now. So we can write it out in full if you want. Like so. All right, so that's how we solve the logistic equation. A couple of remarks. If you don't know the sort of tricks and wiggles, you might end up with a solution that looks a bit different. You might have an exponential here and an exponential here. But if you divide through, you can get to this final form here. I'll make another video about an alternative solution to this, and you can see that, because I think it's quite a common problem. Students work through the problem, and they end up at an alternative form of this solution. So I think it's important to clarify that.